Hey there, good morning, team. Coming at you with some more colligative properties. So we looked at our first one in our last, we split it into two videos because it's probably the longest of them all. So we looked at vapor pressure lowering, right? So if you've got a solvent with a particular vapor pressure, if you add a solute to it, whether it's volatile or not, whether it's an electrolyte or not, doesn't really matter. The vapor pressure of that solvent above the solution is always lower than the vapor pressure of a pure solvent. Okay, we looked at tie lines and fractional distillation, all that fun applications of it. But let's look at the second of the colligative properties for solutions we're going to look at, boiling point. Right? So it was commonly measured and well known that the boiling point of a solution was always different than that of the pure solvent. Why is that? Hopefully this makes sense to you when we discuss why, right? The boiling point of a solution is always higher than that of the pure solvent. Why would the boiling point get higher? Boiling point elevation. Hey, so this is colligative property number 2. So I want to look at why before we start, banging out some, pretty weird calculations. We're going to integrate one of these new concentration units. We were looking at molality into this one. I want to look two ways, two different points of view at why the boiling point of a solution would be higher than that of the pure solvent. Why would adding solute particles, remember it's colligative, doesn't matter what the identity is of those particles. You add solute particles, whether they're electrolytes, non-electrolytes, doesn't matter. And we're going to focus on non-volatile ones. All right, that's going to be our focus. So why would taking a pinch of salt and adding it to a pot of water make it boil at a higher temperature, right? Wouldn't boil at 100 degrees Celsius. That'd be pure water, right? It would boil at a higher temperature than that. So let's look at it from a molecular point of view, right? So shrink our minds down to, hey, if I was a molecule, what would I see? And then we'll look at it from a graphical point of view as well. And then we'll do some calculations on it. And then in a very similar fashion, we'll look at the third colligative property, freezing point depression, which kind of goes hand in hand with this. And hopefully when we look at the molecular point of view of boiling point elevation, you'll see it's just a logical extension of vapor pressure lowering because the vapor pressure is lower above the solution versus the pure solvent. It causes the boiling point of the solution to be higher. If you can think about that before I talk about it in the next board, more power to you. Let's do it. All right, did you think about it? Did you think about it? No math here, all qualitative, from a molecular point of view. So remember our definition before. If you need to go back to the video on vapor pressure and boiling points way back in one of the earlier topics, a liquid, imagine pure water or something like that. Whether it could be a solution, it could be a pure liquid, a pure solvent, doesn't really matter. But it will boil when the vapor pressure above the liquid is equal to the surrounding atmospheric or barometric pressure, right? So when the vapor pressure above that liquid, whether it's a pure solvent, whether it's a solution, doesn't matter. When that vapor pressure, as you're heating it, the vapor pressure increases. So as you're increasing the temperature, sooner or later, the vapor pressure above that liquid will equal that of the surrounding atmosphere pushing on. And if it was 1 atmosphere, that'd be the normal boiling point at the temperature at which that happens, right? And if you're looking at me like, and what are you talking about? You see my mouth moving, but you hear snarg and nerdy. You don't know what I'm saying. Go back and watch that video again on vapor pressure, boiling points, things like that. That will help you remember. Okay, so now that we have that definition out of the way, so when the vapor pressure above the liquid, whether it's pure solvent or solution again, is equal to surrounding atmospheric pressure, it's going to boil. The temperature at which that happens is the boiling point. But if we add a solute to a pure solvent, it reduces the vapor pressure above the solution, right? The vapor pressure above the solution is less than that of the pure solvent, which means it's not going to boil anymore at that temperature because the vapor pressure is no longer equal to the atmospheric pressure. It's lower. Oh no, do you see the logical extension? If the vapor pressure lowers, it automatically changes the boiling point. Let's watch how that happens. So now the vapor pressure is too low. It's not boiling. So we have to heat the solution up to a higher temperature in order to increase the vapor pressure back up to the surrounding atmospheric pressure. which means the boiling point goes up, right? There's fewer particles in the gas phase because of the presence of the solute, physically blocking the liquid molecules, the solvent molecules from getting up. So we got to heat it up higher, get some more thermal kinetic energy in there so we can disrupt those intermolecular forces and get more liquid particles or solvent particles up in the gas phase. And once it gets back up again, equal atmospheric pressure, it will boil one more time. So you might have a pot of pure water, say you had some deionized water boiling at 100 degrees Celsius. Well, you add some salt into it, it might boil at 102 degrees Celsius, 103 degrees Celsius. We'd have to calculate how much, right? It depends how many particles of solute in there. Do you see an equation coming? Yes, you do. Okay. So I also want to look at a graphical representation of this. Remember phase diagrams. If you don't, go back and watch the video on phase diagrams. And I'm going to show you how by adding a solute to a pure solvent, we could take the phase diagram of the pure solvent, the liquid, and see how it changes. Adding the solute actually shifts all the sublimation curves, vapor pressure curves, fusion curves. They all shift. And you'll see because of that shift, automatically the boiling point will change. Let's take a look at that next. It's going to take me a second to draw that. Hopefully this makes sense. This would make a great short answer or short essay question on a quiz or exam. Hint, hint, capital H. Hint, hint, capital H. From a molecular point of view, why does the boiling point elevate for a solution? I'm hoping you could have drawn a phase diagram from memory by now, right? We drilled that in prior videos. So let's just take a phase diagram for any fictitious species or real species. Doesn't matter. It could be water, whatever you want. So here's a generic phase diagram. A little review here. Let's just imagine this is the pure solvent. So, right? And that could be water. It could be acetone. It could be whatever. Got the plotting the pressure on the y-axis, the temperature, not to scale, on the x-axis. And it doesn't have to be degrees Celsius in atmospheres. I'm just putting units in there. Remember, you've got the sublimation curve that separates the solid from the gas phases. Anywhere along that curve is an equilibrium between the two. You've got the fusion curve. I'm not going to label these because that's going to mess it up too much. Our focus isn't on the details of the curve. I'm just reminding you what was there. This is the fusion curve that represents the solid to liquid transition. That would be an equilibrium between them along that line. This is your vapor pressure curve between the liquid and the gas. Anywhere along that would be the equilibrium between them. So you got your liquid phase, gas phase or vapor phase, and solid phase. That is your triple point where all three phases coexist. Pretty cool. And then your critical point up at the top. And then you get a supercritical fluid, et cetera, et cetera. So imagine that's for the pure solvent. What I want to do is look at normal melting points and boiling points again. Let's take a look here. So it would have to be at 1 atmosphere though, right? That would be the normal. So let's say this is 1 atmosphere. So remember what you do? You draw that straight line called an isobar going across. So let's assume this is perfectly straight line. So let's take a perfectly straight line, right? You saw that. That was a perfectly straight line. And let's go all the way across that 1 atmosphere isobar. Well, where does it intersect with the fusion curve? Right here. So if we go down from there in this perfectly straight line, boop, 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 right there, that would be your NMP, your normal melting point, where it melts at 1 atmosphere pressure. Remember? And then if you look at where it intersects with the sublimation, not the sublimation curve, that's down here. This wouldn't sublime at 1 atmosphere unless that was down below here, right? So this is the vapor pressure curve. So take that little line going down. Wada bing, wada boom. That's your NBP, or your normal boiling point, right? Bringing back, getting the rust out of your brain there. What I'm going to do now, let's pick green. Let's do green. Let's show you how this shifts when we add a solute to the solvent and create a solution, right? We're assuming an ideal solution in this case, an ideal mixture. What happens is it shifts the whole thing down. So you'll end up getting your a new triple point. So let's draw a new triple point here. And then the fusion curve will come up like this. Vapor pressure curve. come up like that. And then and we're going to make an assumption that you get just a pure solid at this point, but we're not interested at that. So you get a new triple point, new critical points. So let's do the green one as the phase diagram for the liquid in the solution, right? So let's write that's for the solution. And that is shifted, right? Sometimes you'll see, if I'm running out of time in lecture, commonly I won't show this particular graph. I'll just talk about it from the molecular point of view, which I prefer more. But watch what happens when that phase diagram shifts. Okay? Let's take a look, as the boiling point is determined by where we intersect the vapor pressure curve. Let's have a look at it. Let's do it in blue. Now, where does it intersect? Right there, right? So in that solution, it's going to, at 1 atmosphere, and we can take any pressure we want. We're just doing the normal boiling point. Can you see that that's the new boiling point? Right? So that boiling point for the pure solvent was here. And when you add the solute to it, it shifts the whole phase diagram. And this is the new boiling point. This is higher. So this is a higher boiling point. It was elevated. Can you see that? So it was at a lower temperature, and now it's at a higher temperature. That difference between there and there, that is the boiling point elevation. That's how much it increased. That difference. So that's what we're after. We want an equation where we can calculate the boiling point elevation. Let's call that delta T sub B, the change in the boiling point temperature. It doesn't have to be the normal boiling point, but typically that's what we're discussing unless specified otherwise at some other pressure. Okay? So assume 1 atmosphere pressure unless otherwise stated, and it's going to go up. How can we calculate that? Well, it's going to depend on how many solute particles we put in there, right? It's going to depend on the solvent as well, some characteristics of the particular solvent. May be different if we did this in ethanol versus water versus some other liquid. Let me show you an equation for this. Ready? Now, some of you astute students may go, well, didn't the freezing point or melting point and freezing point being the same thing? Notice the original melting point or freezing point was here. But what happens when it shifts? See how this went down? Uh-oh. The freezing point or melting point went down. So you have a lower melting point. You see that difference? I'm going to draw this graph again in the next video when we do freezing point depression. You see how the freezing point went down? The freezing point was depressed. Oh, but that's for another video. Let's do some math. Yeah. You ready for some equations? And then we can do some calculations. The best part, yeah, to me, the most logical part when you get an equation, as long as you know all the variables except one, you're good to go, right? It's just basic math. Track your units, track your uncertainty. Wada bing, wada bum. All right, so boiling point elevation we defined from the phase diagram was the change in the boiling point. Here for the pure solvent, here for the solution, right? So it increased, it elevated because of the presence of the solute particles. Well, delta means change in, so it's just the final state minus the initial state, right? Final state being the solution after you add the particles of solute, the initial state being the pure solvent. So delta TB will be the solution boiling point, whether it's a normal boiling point at 1 pressure or not, doesn't really matter, minus the boiling point of the pure solvent. So usually that's going to be provided for, although we could solve for either one. Sometimes we solve for the change, sometimes the boiling point, what's the boiling point of the resulting solution? Or maybe I give you that and say what was the boiling point of the original pure solvent. But commonly you're given the boiling point of the pure solvent, especially if it's an aqueous solution in water. You should know that the boiling point is 100 degrees Celsius, the normal boiling point. Let's always assume that unless otherwise specified. How can we calculate that boiling point elevation? Well, what's going to impact that? Well, we know it's a colligative property, so how many solute particles, right? So commonly mole fraction is what we're going to use. We did that with Raoult's law for vapor pressure lowering. But if you've got really, really dilute ideal solutions, like we will be dealing with for boiling point elevation and later freezing point depression, that's proportional to molality. So we're going to be using molality. That's why we introduced it earlier. So if you need to go watch that video. So the amount of solute via molality. So we're going to have the concentration of that solution, which represents the number of particles of solute. And remember, molality is moles of solute over kilograms of solvent. Yeah, temperature independent, right? Watch out. Is the solute an electrolyte or not? Most commonly you read in textbooks, they don't even include the Van Hoff factor because they're dealing with non-electrolyte solutes, where I would be 1. Yeah. But if you're adding a strong electrolyte, I could be 2 or 3 or 4. So I like to insert the Van Hoff factor into the equation myself. And if it's a non-electrolyte, just stick a 1 in there, right? And if you need to review the video on the Van Hoff factor, go for it. Well, also the identity of the solvent, right? So water will act a little bit differently than ammonia, which a little bit differently than ethanol or some kind of ether solvent. So how are we going to represent the identity of that? It's going to be through what's called K sub B. Sometimes I see smaller case K, sometimes uppercase K. I don't really care. Okay. That's the boiling point elevation constant. You'll see the same thing for freezing point later. And that has really funky units, degrees Celsius per molal, per molal, which you could break that up into moles solute, kilograms of solvent if you wanted to. So the whole equation put together, the increase in the boiling point from the solvent to the solution, delta TB, which is that, remember, is equal to the Van Hoff factor, if you need it, right, if it's an electrolyte, times the boiling point elevation constant, which I'll provide for you, or we could solve for it, times the molality of that. So commonly, these are going to be broken up into 2 steps. You could probably do it in 1, but commonly broken up into 2 steps because of that subtraction right there. And I'm going to show you the 2 types of problems. In a second that we run into it, I'll give you that equation, but there you go. So really, there's 5 things in here. There's the boiling point of the pure solvent, boiling point of the solution, the Van Hoff factor, boiling point elevation constant, and the molality of that solution. So as long as you have 4 out of those 5, you're good to go. Let me show you the 2 approaches to this. All right, real quick, here's the 2 most common types of problems you're going to run into. There's variations of them, but fundamentally, and we'll do one of these for the boiling point elevation video, and we'll do the other type of problem for the freezing point depression video, because it's the same kind of problems. The equations are almost identical too. All right, so first one, and probably the most common one, solve for the increase in the boiling point, right? The boiling point elevation, or specifically, what is the boiling point of the resulting solution if you know the boiling point of the solvent, right? So we could say, provided information on the solute and the solvent, i.e. the molality, right? I probably won't give you molality, I'll make you determine it. So I'll give you some information on the solute that's added, its identity, its amount, some information on the solvent, its identity and its amount, and say, hey, if I add this much solute to this much solvent, and the solvent boils at this, when it's pure, what would it boil at after adding the given amount of solute? There you go. That's probably the most common one. And then we could flip that and say, hey, if I give you a boiling point of a solution, right, or an increase, right? So say to increase the boiling point of water by 5 degrees Celsius, or if you want a solution of this solute in this solvent to boil at 241 degrees Celsius, how much of the solute do you need to put in there? So you can back calculate. You can either calculate the molality needed, or specifically, you can calculate literally the number of grams of solute you would have to add to a specific amount of solvent in order to achieve a very specific or needed boiling point, right? So I will do one of these 2, show you the steps. I like to break them both into 2 steps because you have the molality type of information is a multiplication division type problem, kind of a dimensional analysis one. But the delta T is a subtraction, which is a whole different set of units, a whole different set of rules, not units, of rules for tracking uncertainty. So commonly chemists will do these in 2 steps to be able to track the uncertainty. Let me throw a problem up for you. You ready for our first problem? We'll do the first type, right, where we're going to solve for the boiling point of a resulting solution that we're going to make. So let's say, what is the boiling point of an antifreeze solution which is just a mixture of ethylene glycol and water. So you've all probably put this in your radiator or something like that. I even got some from my garage, right? And I live in sunny Southern California, so it gets a little hot here in the summer. I mean, we might get a couple weeks where every day's triple digits, over 100 degrees Fahrenheit. Oh, sorry for swearing. We should use degrees Celsius as chemists. Right? It gets hot, right? I don't want to just put water in my radiator and have that all, boil away if it gets over 100 degrees. That'd be 100. Well, it won't boil, right? We're not going to die, but it would vaporize quite readily. So I'd like to alter it so it doesn't. I don't have to replace it as often, right? And we'll find out in the next video as well that if we depress the freezing point, this is good. If I grew up in Minnesota, it'd get real cold, so it'd be a bummer if you were using water in your radiator and it froze. Because one of the issues we have is if the water froze in a pipe, water would expand and crack the pipes and stuff. It'd be a bummer to crack your radiator. So what we can do is use our chemistry knowledge and add a solute to the water to alter, to reduce or depress its freezing point and increase or elevate its boiling point. You expand the temperature range where it exists as a liquid by adding what's called ethylene glycol, which looks like this. It's got 2 carbons. Imagine ethene, right? No, not ethene, no double bond. Ethane, duh. I'm not an organic chemist. 2 carbon alkane, and just add an alcohol group to each of the carbons. Right? So you get C2H6O2. So we can get the molar mass of that. And here's the density of ethylene glycol, 1.1132 grams per milliliter. Haven't specified a temperature. So let's say we add 820 milliliters of ethylene glycol to 1.5 liters of water. What would be the resulting boiling point of the mixture? Of course, the water would boil as a pure solvent. We're assuming the normal boiling point at 100 degrees Celsius. And you can look on these labels and stuff. I need my old man glasses. Sorry, hold on. Yay, I can read now. So I'm looking on the back here. Yeah, it says it's just ethylene glycol and water. And this one actually says, I'm not doing this one. It says the freezing point as purchased is negative 34 degrees Fahrenheit. And the boiling point is 265 degrees Fahrenheit, 129 degrees Celsius. So that was pretty elevated there. So it makes it very hard. I mean, I've never seen it get to that. I mean, it doesn't matter how hot it gets, right? You're okay with this, but it's going to decrease the amount of the liquid that goes into the gas phase dramatically. And it will help, we'll see in the next video, to keep it from freezing if it gets too cold. And it got pretty cold in Minnesota when I was a kid, man. You walk outside and you're like, forget that, going back inside again. So that's probably the most common applications you'll see for boiling point elevation is using even though it's called antifreeze, you need it in really hot areas. So you don't have to keep refilling the radiator fluid. Not a car guy, as you could probably tell. Some of you are just laughing at me. It's okay, we can calculate it. All right, so we took 820 milliliters of our solute, right? And ethylene glycol, if you look, is an organic species, so it's not an electrolyte, so you can determine the Van Hoff factor from that. And we know the amount of solvent. So let's think about the process, how to attack this. So step 1. I'm solving for the boiling point, so in order to solve for delta TB, I need the Van Hoff factor, I need the boiling point elevation constant, and I need the molality. So we know how much in the identity of our solute. We know how much in the identity of our solvent. So first thing we're going to do is determine the molality. Right? So we know that. So we can get the molality. And then we can, I'm not going to make this a separate step, but we can determine the Van Hoff factor for that solute. And we can, for the solvent water, we can look up on a table. So just anywhere in your book, you can find the boiling point elevation constants. I typed up a whole bunch of them here, right? You might see them on different tables. So here's the solvent. That's its boiling point. There's the boiling point elevation constant, and we'll be using the freezing point and freezing point depression constant later. But you can find a table probably in your textbook somewhere that has very common, especially water, values for that. Once we have the molality, then we can plug it in. So what we're going to do is use the equation I KB molality. So we will figure out the Van Hoff factor from there. Can you see that's I equals 1? We'll look up the boiling point elevation constant on a table. We solve for molality in step 1, and then we can solve for this, and then we're going to use the fact that this is equal to T solution minus T solvent. You see that? We're trying to solve for T solution. So that's why it requires that second step. So use the boiling point elevation equation to find the boiling point of the solution. That's your approach. So I find there's a lot of information on these, so students tend to get confused. So I like to just kind of iron it out and say, do this, do this. What am I given? What am I solving for? Step 1, step 2. Let's have at it. Okay, so let's logically step through this. Get that for me. If you have a textbook, look up the boiling point elevation constant for our solvent, which happens to be water. See if you can find that. And then in step 1, we'll calculate the molality and just plug it in. Easy peasy. You may have done it already, but here we go. Let's do step 1. Let's calculate the molality of the resulting antifreeze solution of the ethylene glycol in the water. Well, molality is moles of solute, which is the ethylene glycol, over kilograms of solvent, which is the water. Okay, well, let's take the information we have on the solute. What were we given? 820 milliliters of ethylene glycol. I'm just writing glycol. You could put EG, or you could put C2H6O2, whatever you want. And how much water were we given? 1.5 liters of water. So that's our starting point. So what do we got to do? I got to get milliliters of glycol to moles of glycol in the numerator, and I got to get liters of water to kilograms of water in the denominator. And then I'll have moles of ethylene glycol per kilograms of water, and I got the molality, and I can plug that into step 2. I have a meowing cat. I don't know why he's meowing. All right, so let's focus on the ethylene glycol first. I need moles, which we know how to get to from mass, but this is volume. How do you get from volume to mass? Density! Didn't I give you the density of this? I did. So look up on your little thing there. It was like 1.1132 or something like that. Is that right? So let's use the density as a conversion factor to convert milliliters of the glycol, ethylene glycol, to grams. So I believe that was 1.1132 grams per milliliter. I'm going to put EG for the glycol, ethylene glycol, and milliliters cancels out there. However you want to label the ethylene glycol or glycol, it's up to you. So now I got it in grams, and we know the formula, so we can convert grams to moles. All right? So for every mole, what was it? C2H6O2, is that right? Let's figure out the molar mass of that. So get your trusty dusty periodic table, right? So we got 2 carbons. Mine is 12.011. So 12.011 times 2 equals, good to 3 decimals, plus hydrogen 1.00794 times 6 equals, plus, hopefully I don't screw this up, oxygen 15.9994 times 2. So I get 62.06844, good to 3 decimal places. Boop. Nope, I can't get my lid off of my pen. So I see 62.068 vertical dash line 44 grams per mole, right? Good to 3 decimals because the carbon value I used of 12.011 was limited to 3 decimal points. So that allows us to cancel out grams of ethylene glycol. And we've got moles of ethylene glycol, solute on the top, yay! So now in the denominator, we got to get, so check. Boop. Let's get liters to kilograms. Well, that's volume to mass. We need density again. Oh no, you say. Density was not provided. So remember, if the density, because with temperature, if temperature was specified, we could probably do a linear interpolation and figure out the density to 4 or 5 significant digits. That'd be great. But we're only 2 significant digits here anyway. So we can just approximate the density of water. We know it's about 1 gram per milliliter. You're probably at least good to 2 significant figures. So let's assume 1.0 grams per milliliter. Now, isn't that the same if I multiplied the top and bottom by 1,000? That would give me kilograms per liter. Ooh, kilograms per liter. Do you see that? If I multiply the top by 1,000, I get kilograms. If I multiply the bottom by 1,000, I get liters. So I could just say 1.0 kilograms per liter and go directly from liters to kilograms. So let's go like this. I want liters of water up on the top. And I want kilograms on the bottom. So we're going to say 1.0 kilograms per liter. And you see how the liters of water cancels out? And this would be for the water. And my resulting units are moles of solute per kilogram of solvent. That's my water on there. I ran out of room, but if you want to write water on there, limited to 2 significant digits. So I'm going to pause this so you can calculate that and bring that number down and give me the non-rounded value to 2 significant digits here, limited across. So we didn't need the density quite to that degree of accuracy. And then if you would kindly just take that molality, plug it into the boiling point elevation constant equation that I gave you, and see if you can solve for the boiling point of the antifreeze solution. See if you get what I get. Ho, be right back. Real quick, is this what you got? Let's double check our molality. When I go through limited to 2 sig figs, I get 9.804 moles of ethylene glycol per kilogram of water. Or you could just, instead of writing all that bulky stuff, just go 9.804, good to 2 sig figs. Molal, right on. And remember, don't round that. I didn't ask for molality. I asked for the boiling point of the resulting solution. So don't round that until the very end. Let's plug that into our equation and have at it. All right, let's take a look. We know that that is a non-electrolyte. So for ethylene glycol, I will be equal to 1. A lot of people just leave it. A lot of books will just leave it out of the equation directly. So we need a table to find the boiling point elevation constant. So probably in your textbook or something. So mine's on the bottom here. See water, right? The boiling point of we're assuming normal boiling points, 100 degrees Celsius. So the boiling point KB, elevation constant in degrees Celsius per molal, is 0.512 degrees Celsius. Do you see that? 0.512 degrees Celsius per molal. So you just look that up. And I'll either give that to you in the problem on exam, but I'll probably give you a table like this on the end, so you have to fish it out and find it yourself. So for homework, just look in your textbook. You probably got a table for it. So we know I, we know KB, we know M. We can solve for the boiling point elevation and then extract. Don't forget to extract from that. I didn't ask for the boiling point elevation. I asked for the boiling point of the solution. So this will be 1, right, which is an exact number, is unitless, times KB, which is not exact, 0.512 degrees Celsius per molal, times the molality. What was that, 9.804? Was that right? 9.8, good to 2 significant figures, 04 molal. Do you see how the molal cancels out? Bye-bye. And you're left with just units of degrees Celsius, which is good because we're dealing with how much it elevated in the temperature. So let's punch this out real quick. So let's take 0.512 times 1. I can do that in my head. Times 9.804. You get 5.019648, on and on and on and on your calculator goes. So that will be equal to, let's see, 3 limited to 2 significant figures, right? Because that's exact. So 5.019 degrees Celsius. So that's how much, if you looked on the phase diagram, it increased 5.019 degrees Celsius. But we want the boiling point of the pure solution, and we know the boiling point elevation is temperature of the solution minus the temperature of the pure solvent, right? Final minus initial. So the boiling point of the solution will just be the boiling point elevation plus the boiling point of the pure solvent, right? So take whatever the boiling point is for water, and if it was, I would expect you to know that. Anything other than water, I'd give for you, or you can just read it from my table I give you. Right? Plus, so we're going to take, and we know that's 100 degrees Celsius, so let's take the non-rounded 5.019 degrees Celsius plus We're going to assume that's exact by definition. 100, right? So that'll be 100.5. No, 100. I can't do basic math in my head, can I? 105.019. If that's exact and we're adding, we're limited to one decimal place here. So 105.019 degrees Celsius. And then that won't round up, so it just goes to 105.0 degrees Celsius. So by adding that much ethylene glycol to that much water, it's going to boil at 105.0 degrees Celsius rather than 100 degrees Celsius. So I don't have to refill my radiator as often. Yay! And in the next video, we're going to do freezing point depression, which is going to be literally exactly like this, but we'll do the other kind of problem. We got it!